person now standing between you and the lunch. I try to make it as exciting as possible, but let's have. Okay, I'm actually talking about transition in urban water systems from a modeling perspective, but I will add quite a lot on what Anna has been telling already, not repeating too much. First of all, introducing, does it work? Down. The other way, okay. It's a work which has been done over some years, also in Innsbruck and in Monash, and I'm simply citing all the persons who have contributed here. What do I talk about in more detail? First, I would like to introduce a little bit about why do we actually need an integrated view on this issue. I would like to start from a historical perspective and outline a few of these reasons why we have to look into this issue from a very complex and integrated view. I'm going to talk very little about this integrated model concept, which has already been introduced, and then I go into some details about some phenomena, technology transition, urban development, and the last one is about network placement, which then is coming back on where do we actually have our sewers, this relation between road network and the different types of networks. If we start to discuss modeling issues, we need to have, in systems analysis terms and model structure analysis, our playground is this town, alpine town of Innsbruck. We use that because we have all the data. It's not a particular huge thing. It's a 120,000 inhabited town, and it's bounded by physical boundaries like this mountains here, which sort of prohibit an extension. So urban sprawl is not something which can happen, at least not in large scale. But it's interesting, and the interesting thing, as I said, is that we have a lot of data in historical terms, that the development of the water supply network all the way from its start around 1900 all the way to today. We have the same data for the drainage network here from Innsbruck. I'm usually talking about the drainage network. This time I would like to talk more about the water supply. One of the first things which we see if we look at the development of these networks, that we have a complete misconception between the planning horizon and the lifespan of such a network. So the lifespan of such a network, okay, in the average times, it's the same, roughly 50 years. But some of the pipes, they survive quite a long time. So some of these pipes, both from the water supply and the drainage aspect, they are since the beginning here in the system, which means they are influencing the layout of the system until today. And if you go back now to the planning, these guys who have introduced these systems around 1900, more than 100 years ago, they had maybe a planning phase, a projection phase of 50 years, but that already would have put them into 1950, and in between we had seen two major wars. Probably they couldn't anticipate what happened in the system. But what actually happens now that these systems, these guys have designed, they are still in place in today's system, which is completely out of their perception when they started to plan these things. So we have to realize that this is a huge misconception, and we have to see this long lifespan of our infrastructure as an issue which we have to deal with. Some other things, there are many things we could talk about, but just two small issues. Water supply system now. The construction phase and the design, the original design, was based, of course, on metering. So people knew how much water was taken, but the water was taken sometimes from running waters. People had to carry some of the stuff, and it was a nuisance. It was not so easy. So the pipes were introduced, and suddenly it didn't really fit with what the original planning was. Why? People knew for example, had all these facilities. They just had to screw the tap and the water was running. So they used approximately twice as much water as they had in the original phase. So simulation, historical, from the history, we have an US EPA net, and this is the pressure distribution in the system based on the design load. Everything works, nice, wonderful job, at least from design phase, but this is what actually happened. And what you can see here is that the large region now, the pressure is not sufficient any longer, simply because the people use too much water. Okay, other thing that we have seen quite often, roughly in 1980, you could actually see, do we have the thing here? Yeah, perfect. You could see the water consumption in the whole system constantly rising. So people have been knew that they have to do something about the future design, and they made a projection, and that straight goes up here. What happens in reality, we've seen that quite often, it simply goes down. Why? Two reasons. In Innsbruck, the population suddenly was stable, so the steady increase was stopped here. Various reasons, don't have to go in details. But second thing was also a complete change in technology, in water-saving technology, which changed the picture. Okay, what do we learn? First, lifespan of the system makes planning really uncertain. Second thing, urban development drives the layout of the water system. It could sometimes also be that's the other way around. We have heard today already some analysis about the vicinity or the development of a city in relation to its water resources. But for the layout of the network, the urban development is really the decisive factor. Technology development is unpredictable, of course, within physical boundaries. But if you just think about somebody planning in 1900, for example, water treatment systems, he could not anticipate something like membranes or photocatalysis or other fancy novel solutions. And the last thing is socioeconomic is really essential if you implement new solutions. And our conclusion was that we need to model this urban water cycle as an integrated part of the city, and that was actually the title of the workshop we had 2 years ago. And Christian and me, here, we had a paper where we sketched here how such an integrated model should look like. It's the pressures from the society, from population growth, from climate change, and that needs to be taken up by such a model. So we need a societal model which could be predominantly it's agent-based model here, basically representing the stakeholders of the system. And then we need to do something about the development of this urban form, and that's done in terms of procedural modeling, an algorithmic generation of this urban form. And then, of course, we need to implement all these networks and the pressures, and that has already been told by Anna, how to do that. But that was too fast now. Okay. Where have we been here? So, one example, I don't want to go into that, but such a network has been presented, Dance for Water as a tool. I'm now going into some of the more detailed procedures and processes which have been implemented in such tools and how we can implement it actually. First is technology transition. So if we discuss technology transition, there's a whole field in itself. That's the common theory. You have an innovation, you have an initial diffusion, and you have a sort of a logistic growth curve until a technology is really diffused into the society. If we try to implement something like this in our models, because we need it, if we make, if we model into the future, so we have to deal with the changes also in our technology. then we cannot avoid that we need as a background, as a basis, something like a scenario workshop. So that's actually a theory which has been developed in Monash from the socio-economic group there. And the key is that we start basically from our current system and envision how a future system could look like. And that is a detailed process. We don't have to deal with it now in really detail, but it's a process where you need to gather a number of stakeholders. You need to have certain scenarios which you have to test all your theories with. And once you know where you want to end or where you're likely to end with which kind of technologies you're implementing, you can then backcast this and point out the transition pathways which are then going back into the model. That could be also happen in a rather short way. You could do it yourself. Then it's a rather limited workshop, but you cannot avoid to sit down and really define technology transition, the basis, because the model itself cannot develop any kind of technology change. It's not possible. So you need to put that into the model as a background information. Once you're there and you know which kind of technology you want to implement or which kind of technology change should be implemented, then there are different models how to do that. That's the most simple one, and that's an enforcement by technical guideline. For example, if you have a drainage network, runoff system, each time you do some kind of changes in the system, you could then enforce that the drainage is no longer going into the pipe, stormwater, but it's infiltrated. Or water supply, each time you renovate the building, rainwater garden, rainwater harvesting has to be implemented. In theory, okay, that's just would be a completely typical system. You could then end up with a linear implementation, but that's only theoretical. So in practice, you always end up with a curve. But that's not really a model. That's a very, very simple model. Basically, it's just one line in the code. If, then. Yeah? But it's quite helpful because it really outlines if you have a system which is mainly driven by guidelines, it happens a lot, for example, in Central European systems, then this one is really very helpful. On the other hand, if you have a system which is more open, which is based, for example, on more marketing strategies where you have to sort of convince people how to adapt and how to implement the system, then you really have to go into transition theory. There are different schools. This is a theory which comes, it comes from Monash University, originally also connected with theories from the Netherlands. And it's a model where the development of different methods and different views on, of technologies are modeled in terms of agents, but they are called here constellations. What is, you can see, I'm always getting this wrong. What you can see here, that you have constellations. This one here, for example, is representing a decentralized strategy. And here you have another one which is channelized drainage. That's more a classical approach. And this is then also bounded by constraints. You also have, you need to take into account what is the general what are all the influences on this model. And with time, these constellations are then growing or shrinking. So that can be, for example, explained that simply by the size of these constellations, they are representing the power, if they are more dominant in or not. If they are more dominant, it's more likely that people will introduce some of these solutions next time they have to change something. Okay, in the end, you can see that we have, for example, here a system like it could be today, centralized water supply, centralized sewage, centralized drainage, and you have here smaller constellations, smaller types here, stormwater harvesting, decentralized wastewater. And now in the view of outside influences, could be from the society, from economy, it's also about how cheap are these solutions. Then you get possible futures. Could be that you end up completely in a centralized system, even more as we have today, or it could be the other way around, that these centralized ideas are shrunken, they are less important, and suddenly these decentralized strategies get much more important, gain in power. Okay, so what we get out in modeling terms is a stochastic model result, because this is a stochastic model, and that makes prediction a little bit more complex. So you have the huge number of outcomes, and you need to cluster it together in order to get some results out of it. As you see, it's a fairly complex model as compared to the other one. There are, of course, models in between where this could be sort of taking up these ideas. That's a fairly complex model, as I pointed out before. Next issue, urban development. It's about the change in land use and in population, and I bring again an example in the vicinity of Innsbruck. That's a small settlement very close to where we are. Here is the university here, and that's how it expanded within 50 years. And you can imagine what changes that caused to the water infrastructure, and it's very important, again, to discuss urban development in such models. Again, we need some baseline. We need to have a master plan. We need to have some ideas. If coming back now to the Melbourne case again, we need to have some ideas if Melbourne will have in future 4 or 5 million or 8 million inhabitants. And we need to know where they will be implemented, where will be the major amount of these people be situated, otherwise it's not working. A model in itself cannot dream of future, it needs to have some guidance. We have again 2 different models. That one was developed by a PhD student of mine. I'm not going here into this circle, I will explain it immediately. It starts that in a way that we have to come up with a prediction of the population changes. Yeah? In that case here, we have a population increase in Innsbruck. That's a stagnant period, which I talked before, and now we are going to see an increase again in the next 50 years. Could be also a decrease, but increase is here in that case happening. So again, what we need as the next thing, we need to have a spatial translation of the master plan. So you can see here the different parts of the city which are opened up for buildings, and we have here also a timeline how this is going to happen. The model in itself goes in, zooms in, we have all the data, orthophotos, spatial plans, and this is really strange. Okay, so the model zooms in, sees how big this system is, what can be built there, and that is now what we call procedural modeling. So based on information, which type of models, which type of buildings should be implemented, industrial buildings or more housing, different types of buildings are then implemented. Of course, it has to correlate with the amount of people you have to accommodate here. So once this is given, we can run that through the timeline, and what we get here are changes in the system. So we get changes in the amount of people living in certain areas, but also a reflection on changes, how the impervious area, for example, is changing and developing over the years. And that's actually what we need as a result for our network transition model. The same thing you can do in more complex terms. You could use one of these models which are available, state-of-the-art models for urban development. That is Urban Sim, which has been used in Dance for Water, development from the University of California. And I don't want to go in detail, but it's just the next level of complexity. It deals with stakeholders, for example here, developer who build new units. Then it deals with the households. For example, if a household is prone for flooding, then most likely the household would like to move away. So they want to resettle, and then they are looking for opportunities where it's nice to live, and then this water sensitive city comes into play. If there's a nice environment, green environment, so this household will most likely want to move there. Background, we need an awful lot of data. We need to have data not only on the individual grids, on the plot, on the residential units, but we also need extreme detailed data on the individual households. Also, for example, income data. And unless we have all this data, these models are more or less useless. It doesn't help to have an extreme complex model if we don't have the data. Then we are just guessing. So we might as well use a simplified one. So these models are fantastic, but the amount of underlying data we need to really drive it forward should not be underestimated. Once we have it, it's really a nice tool to get all the information out. That's again the same paper which is in line. Oh, no, I think that one was published. That's the water research paper, yeah? Okay. But it's the same story basically from Innsbruck, where the different master plans evolve, and we can see the changes in the system. Last thing, I'm coming back to a question which has been raised beforehand. It's about infrastructure and infrastructure placement. Where are the networks situated? If we make planning into the future, then we need to know where these systems evolve, these network systems. If we don't have any information, we need to come up with a conclusion, basically a virtual network. Surrogate data, I think we are, it's a common concept that the best surrogate data which we can derive or which we can use is street network data. First of all, we have it openly available, open street maps, much better information than we have from the networks itself. But we can also, in terms of future perspective, it's easier to sort of forecast a street network from the urban form. We did some work on multi-utility network similarities. We made geometric analysis and also graph-based analysis. The two graph-based indicators was closed loop indicator and leaf indicator. To look into that, the geometric analysis, for example, that came for 3 different case studies, came to the conclusion that roughly about 80% of the network, water supply and sewer, can be found below the streets. And that's why we usually talk about our 80% papers or our 80% approach. That's just a magic number which we came up with. But that's something which was fairly resistant in all the situations which we investigated. So if we have that, we can turn that around and can also use the graph-based analysis, which is based on the minimum spanning tree. minimum spanning tree. Let me go back once again just to explain it in one thing. If you have a loop like here, the minimum spanning tree is basically the pathway to get to all knots, but using the minimum weight in network theory, in graph theory. So we can use this this approach. We need to have a street network. The digital elevation map, for example, for water supply systems, is only needed for the design purposes, because we need to know where the demand nodes are situated in order to get a view on the pressure. We need to know about the reservoirs, and we have to have some information about the demand nodes, how they are situated and where they are situated. If we have a very good information about that, then it would be a semi-virtual network. If we don't have any clue, then we simply can distribute it uniformly, and then it's more likely to be a virtual network. The more information we have, the more realistic it gets into what we call a semi-virtual network, of course. How does it work? Okay, this is the system we investigate. We have a street network here, then we add these tanks, and then we have the minimum spanning tree, which is connecting the two tanks with all the streets in this way, like I said before, the minimum spanning tree. That is then sort of correlated with the demand nodes, and all the parts of these networks where no demand is needed are cut away. And that is what we then end up with. This is a minimum spanning tree of a water supply network where everything is connected by a realistic layout based on the street network, but without any loops. And then you can add these loops, again based on this graph theory, and can use this one here to create a more or less looped system. It works nicely. This is the original network from Innsbruck, and this is the minimum spanning tree here that already has fairly good results, but it's not looped in any means. And then we have here two different loop systems, one with a big main loop, and that one with a very small loops here. In the end, of course, we do not get a complete overlap, but we get systems which work in similar way as the original system. We used that one for an example. It's a fairly famous example. It's a town in Sweden, Kiruna, which is undergoing a major change in that way that the major part of the city is actually relocated. That's a mine here, and the mine will take away here a large part of the existing city, and that has to be moved into a new city center here, or a new city part. And one of the things we did was that we looked into the water supply system that's based again on a digital elevation map and the street network. Here are the water sources, and that's the demand distribution here, and we coming up here with a new generated, it's a semi-virtual water supply system. I'm not showing here what we have been doing. It's Jonathan's work. He has it also on the poster, where the dynamic of the temporal dynamics of the water supply system is simulated and analyzed. One word of caution. Engineers and modelers like to play games, and we are sort of fall quite often in the trap to play SimCity. And we have to be aware that these models are not classical deterministic models in the sense that you can really make a calibration validation study. What we could do is sometimes to make something like a validation. You have seen that picture before already, or at least this one here. We could make some comparison between observed and modeled systems, but in terms of really a stringent calibration or even validation of these models, it's not really possible, and we end up what Anna already explained. These are scenario tools for development of ideas, of possible futures, and not really strict model, deterministic model results which we can directly translate. Coming to the end, for what we have learned is that infrastructure transition must be seen as a very complex issue, and at least if you go in details, if you go away from a statistical analysis, what's happening with these networks, if you really want to make predictions, you have to treat this in a very integrated view. You have to take into account all these connections, otherwise it's not working. The most important thing is to take into account urban development and socioeconomy. It's the decisive factors for these transitions. We have different model concepts. I hope I was able to show that the most complex one is not always the best one. It's a data problem. The huge uncertainties involved, especially with the urban development model. We have huge data issues, and sometimes it's better to guess and take a simpler model instead of providing an air of being exact when the underlying data is simply missing. And the last thing that is to be realized, that traditional approaches for validation and calibration have a very limited meaning for these type of models. Thank you for your attention.